seminar series with the talks about permafrost issues also, and definitely, obviously. And the first speaker will be Costanza Morino from the Université Savoie Mont Blanc, from France, with the topic tracking the degradation of mountain permafrost with molards. Go ahead. You have 12 minutes. Sorry, not 20. 12 minutes. Get started. Yeah.
Thanks, Vasily. Can you see my screen?
Yep.
Excellent.
Works perfectly.
Awesome. Thank you. So, hi, everyone. As Vasily said, I am a postdoc at CNRS, working at Laboratoire Edytem and Université Savoie Mont Blanc. And today I'm going to be talking about a landform that might not be that you're not that familiar with. They are called the molards, and this talk will be about how to use them in tracking the degradation of mountain permafrost. So first of all, what are molards? Molards have been defined in the literature as conical mounds of debris on landslide deposits. In previous studies, they have been described in the various landslides. I've reported some examples here from the Sherman landslides in Alaska and the Brazeau slide in Canada. And they have been described in the field, but they remained sort of puzzling for scientists who couldn't always recognize how they formed until recent years, when people started to infer that they could be related to permafrost degradation. For example, in Argentina, the molards were linked to the release of a landslide that originated from a rock glacier. So there were some ideas about the relation between molards and the permafrost degradation. So why we started to study this landform? Because we found them into landslides that occurred in northern Iceland. The first case study that I'm going to show you is the Moth-Eternal landslide that occurred in 2012 in the Tröllaskagi Peninsula in northern central Iceland. And the second case is the Arnarfjall landslide that occurred in 2014 in the West Fjords of Iceland. What occurred in these two events? So basically, the two events were characterized by the release of frozen talus deposits. In this picture, you can see blocks of ice-rich sediments that were photographed immediately after the occurrence of the first case landslides. These are blocks that are perched on the topographic bench from where the landslides originated. So we have here still some of the source deposits are still frozen in the form of blocks. And this is one of the biggest blocks that we found in the deposits of the landslide, and you can see that it has this beautiful angular shape, and this is due to the fact that it was completely ice cemented during the failure. This is the same block degraded into a cone, and this picture was taken 3 years after the occurrence of the event. So we have a cone of debris that is the remnant of the block of ice rich sediment that originated from the Moth-Eternal landslide. The second case is the Arnasfiat landslide that you can see again originated from talus deposits perched against the north-facing rock wall of the Arnasfiat mountain. Again, we found immediately after the occurrence of the landslides these angular ridges that have this shape because ice was preserving this angular shape. And if you look at the same area now, it will look like this image. This was taken 2 years after the occurrence of the landslide in 2016. You can see that those ridges have degraded into a much more conical shape due to the fact that ice has thawed. So what we did was to study the morphometics of these molards to understand what were the processes that brought to their emplacement. And we found in the first case study that first of all, the molards are all perched at the foot of the talus slope below the main scarp in this flat area here. They do not, their longest axis do not have a particular orientation compared to the longest runner direction of the slides. And this indicates an origin via free fall. Instead, in Arnasfiat case, we have a different situation. We have all the molars that are perched just below the main scarp, and their longest axis is perpendicular to the longest runner direction of the slide, indicating a tilting downwards that is due to coherent movement downwards. So two different processes, two different origin for the same landform. And in terms of dimensions in Morphotuna, we have a much more heterogeneous size due to the fact that you can have different sites of blocks originating from fall, while in Arnasfiat we have much more homogeneous size due to the fact that we have this coherent tilting downwards. In terms of shape, the Morphotuna ones are more circular compared to those in Arnasfiat, which is again due to their these two different gravitational processes. So we can firstly conclude that molars in periglacial environments derive from the degradation of blocks of ice-rich sediments into cone of debris in landslide deposits, and their distribution and morphometics help us in identifying how the landslides dynamics processes. So we started from these and we asked ourselves, okay, is it possible that we can identify molars in other places, at other locations? The answer is yes. We have identified several cases of molars on landslide deposits in areas where we have either discontinuous or continuous permafrost. I'm sure that you are very familiar with this figure. We also even have identified very, very recently a case in sporadic permafrost in the Alps. So I'm just going to quickly show you some cases. This is, again, Iceland. This is a very recent landslide that occurred in northern Iceland. And you can see that, again, we have conical features scattered in the depositional area of the landslides. And a very interesting case is located in Greenland, where we have several rock avalanches in the Vega Strait, which is located in the western coast of Greenland. And you can see that, for example, here we have mollards that scattered the depositional area of this rock avalanche, some of these rock avalanches. And this is a very prone, landslides prone area. In fact, we have quaternary sediments underlying basalts, so a very densely landslides prone area. And in the map here, you can see that mollards fields are conspicuous in this area. Mollards fields are those marked in purple. And here we have a nice field image of blocks still cemented by ice, transported by another process, in this case by a debris flow. And finally, to just quickly conclude on other environments, periglacial environments where mollards can be found, this is the surface of Mars. This is Hale crater, and in the left image you can see an ejecta flow with the arrows indicating the direction of the flow, which is scattered by conical features. And since this area of Mars is thought to be rich in volatiles, we inferred that these conical features might be candidate for mollards. And the final case example that I will draw to your attention is on Mercury. This is a paper published by Bright et al. In 2020 on EPSL, and these are we are in the Caloric spacing, and these conical features might be similar to mollards, as again in this some of these conical features present hollows, and which might be sign of loss of volatiles. So again, we have a potential analog, planetary analog for mollards. So to conclude, we definitely need a better understanding of how mollards form, how they can evolve in time, and this will be done by studying their morphology and the timing in which they form, and the environmental setting in which they form. And this is just to show you that molar can be used in periglacial environments to understand climate change and hazardous phenomena related to gravitational mass movements. Thank you.
All right, thank you. Thanks a lot. And we start with the questions. Do you guys have questions? You can use the chat, or you can ask straightly to Costanza. Do you have any questions? Yeah, I can start. I just have a simple question. So you just showed us a map of the mollards all about the world. So it was Iceland, Alaska, and other places. And did you try to find mollards or related forms in any periglacial environment? So was it the spatial analysis, or what was it? Because could it be formed like in mountains of Siberia, or I don't know, like in mountains of continental America? Yeah. So just...
Yeah. So definitely we found mollards not just in mountain environments, of course. Being mollards landform that is connected to landslides, that you need topography to form a landslide. So mountain environments are obviously the best. But we did find mollards also in Russia, in areas where permafrost is not, it's only sporadic. So yes, there are examples of molars that are not just in continuous and discontinuous permafrost.
Is it the object of the future studies? Am I right? I mean, just generally.
Yeah, no, this is the work I presented here is a part of a big project in which I am involved, and that is focusing on the study of this landform from different perspectives. So from an experimental perspective, a field and geomorphological perspective. Yeah, so different aspects of.
Thank you. And question from the chat from Kate and Kelkar. Great presentation. Which specific methods do you plan to use to characterize degradation of internal ice in molars?
Oh, good question. So as I said, experimental work is probably the best option for that. Characterizing the degradation of internal ice might be very difficult. And probably we have plans for also some modeling of the degradation of molars deriving from the experimental work, but that is, internal ice might be a little bit hard to characterize, if I answered your question.
Thank you. Another question, second question from Kate and Kilker. Do you plan to compare surface temps and temps derived from molars?
Yes, so if it's that ground temperature, the long-term plan will be to probe ground temperatures and do some permafrost modeling in the areas affected by molars. We have plans for doing so in Greenland. Unfortunately, last year we couldn't go in the field, and probably this year neither. So that is a long-term plan. In terms for measuring temperature within the molars itself, it's a bit, it won't be that indicative of permafrost degradation because the ice has already degraded and it's superficial. So it's the plan is to study the degradation of the ground temperatures rather than those on the already degraded mounds.
All right, thank you for the detailed answer. Do you guys have another questions? We can use the last option. No? Yeah, just a brief question from me also, because super interesting topic. And have you ever found molars on the existing glaciers? So could it be formed? So could it be like a part of landslide that was just slided on the glacier?
You mean supraglacial landslides?
Yeah.
Not there are not recent cases that I am aware of, but the Sherman landslides, which when it occurred, the authors that described the Sherman landslide did found conical mounds on that landslide. Obviously now it's completely degraded and transported by the glacier, so you can't see that. But that's the only case that's come to my mind where there is this case.
Thank you. And the last question from Edwin Emmer. Do you plan to do some more ERT surveying?
No, Adriana, we don't have any more plan for doing ERT surveying, but it would be good to do some.
All right, cool. Thank you, Costanza. We're going to the next speaker, Meven Philippe, with the topic Insights from Preferential Distribution of Polygonal Pattern Ground on Mars. We're moving from the Earth to Mars. Using definitely the Tesla X site, probably, or another one.
Hey everyone, can you hear me?
Yeah.
Okay, excellent. And can you see my screen now?
Sure.
Okay, excellent. Thank you very much. So yeah, thanks everyone for coming here to hear my talk, in which I will present you two studies, one which is already published and one which is in progress. And both will be, as Valdez said, about the insights we can get from the preferential distribution of polygonal pattern ground on the planet Mars. So I assume you all know what polygonal pattern ground are. They are very common features on Earth in periglacial environments. You can see it in the panel A here, and they result from the thermal contraction of icy ground. Sometimes their margins can be underlain by sand wedges or ice wedges. Globally, the wedges are features that grow seasonally. In case of the ice wedges, it's with water flowing and refreezing in the cracks. In case of the sand, it's with sand refreezing in the cracks. So when these wedges are developed, they cause the margins of the polygons to uplift, which forms polygons with the center relatively lower in elevation than the margins, so low-centered polygons. That's the panel A, where you can see pounds that formed in the polygons. When those wedges are degraded, it causes the elevation of the margins to reduce, which forms high-centered polygons. That's the panel B. For the moment, I only showed you photographs taken on Earth, but you can see on this one that we see similar polygonal pattern ground on Mars, with presence of low-centered polygons pointed out by the blue arrows, and high-centered polygons pointed out by the red arrows. Moreover, we know from various observations and measurements that there is ground ice in the subsurface of Mars. Here, for example, you have a global map of the concentration in water ice in the ground, constructed by the data from the gamma ray spectrometer on board of the probe Mars Odyssey. Obviously, you can see that polar regions host more ground ice than the mid-latitude. Another example of ground ice observation, or ice observation at least, you see that in these two craters, you have massive deposits of ice. So on panel A, it's an unnamed crater, and on panel B, it's the Korolev crater. Both images come from the high-resolution stereo camera on board of Mars Express probe. Then, a last one. When the Phoenix lander landed on Mars in 2008, he bounced on the surface, digged a small hole, and then took a picture. And what we see here is small deposits of water ice that were covered by the regolith. Just for you to explain the right part of the picture, a few days later, so 4 Martian days, these water ice deposits started to degrade progressively. However, how it's written here, Mars is not supposed to have hosted liquid water in the past billion years. So it brings up a question, which is, what is the formation mode of the Martian polygons we observe? For the first study I told you about, we retained two hypotheses, the ice wedges and the sand wedges. Those two hypotheses have totally different implications, as if the polygons we observe are underlain by ice wedges, it implies the recent occurrence of 3 thaw cycles of water in the recent part of Mars. As I said, it is not supposed, and it would have very important implications in terms of extraterrestrial life and habitability of the planet. But also, ice wedges imply the current presence of massive water ice in the Martian regolith under mid-latitudes. And this, this would be of great importance for the future colonization of Mars by the humans eventually. In contrary, the sand wedges do not imply recent freeze-thaw cycles of water on Mars, neither has the presence of massive water ice in the ground. Something to differentiate between ice and sand wedges is their stability. Indeed, ice wedges are supposed to be more stable with increasing latitudes, thanks to the decrease in temperatures. And this is something that is not expected for sand wedges. So in the first study, we chose the study area in Utopia Planitia, which is one of the great plains in the northern hemisphere of Mars, which is well known for containing numerous units of polygonized, units, sorry. On this study area, we collected 119 high-rise images. These images are high-resolution images taken from the orbit that can go down to 25 centimeters per pixel, which is very cool. We then divided the study zone into two terrains. First, the plains, which represent basically the whole study zone, excluding the terrain type 2, the craters. We made this distinction because previous works have concluded that craters, with their lower elevation compared to the surroundings, their higher atmospherical pressure, could act as cold traps. Then we gridded our images into squares of 500 meter by 500 meter. And in each square, we mapped the presence or absence of high-centered and low-centered polygons, what you can see here on panel B. Then for each degree of latitude, we computed the ratio number of squares containing high-centered polygons, low-centered polygons, sorry, on the number of squares containing high-centered polygons. This parameter acts as a, let's say, a proxy for the stability of the wedges. As results, we analyzed 33,351 squares, which was quite long. And we observed that when considering both terrains, so the craters and the plains, no correlation was observable between the latitude, here horizontally on the diagram, and the ratio low-centered to high-centered polygons, here vertically. However, when considering only the plains, so when excluding the craters that may act as cold traps, a statistically significant correlation appears between the latitude and the ratio, as you can see here on panel B. Therefore, we suggested that the polygons of our study zone are ice wedge polygons, with all the implications it has in terms of freeze-thaw cycles of water and presence of massive ground ice, as I mentioned before. Then, the end of this study brought up a new study, because during the mapping, we observed that the polygons seem to concentrate on a sinuous unit. This unit is outlined here in blue, and it appears bright on the thermal infrared data we have of the surface of Mars. So I called it the bright unit. On this figure, you can see that the black boxes represent the high-res images we analyzed, and the red dots represent the squares with polygon of each type. And it's visually striking that the bright unit concentrates the polygons. This brings up a new question, which is how and which regolith properties could favor the ice wedge formation and preservation, talking about, for example, this bright unit. So first, what we have to do was to reduce the study zone to the latitudinal ranges that contain both the bright unit and high-res images on this bright unit. Then we divided this new study zone into two terrains. First, the bright unit here in blue, and the surrounding terrains here in green. We then reused the data from the grid mapping of the previous study to compute for both terrains two parameters. First, the percentage of polygonization, which is simply the percentage of square on this terrain that contain polygons of each type. And second, the ratio low-centered to high-centered polygons, which is the same parameter as for the previous study. We also compared the thermal inertia of the two terrains. As a result, we saw that the bright unit shows a high percentage of polygonization, around 90, compared to the surrounding terrains, around 50. It also shows a higher ratio low-centered to high-centered polygons, so 0.24 again, 0.50. However, the thermal inertia of the two terrains cannot be distinguished based on the scatter in the data, which means that the thermal inertia of the terrains alone cannot explain this difference in terms of percentage of polygonization and ratio low to high-centered polygons, which led us to conclude that the polygon density and type can provide insights into the capacity of a regolith to favor both grandize development and preservation. And here I'm talking about parameters such as the grain size or the porosity, which therefore gives an information on the geological origin of this regolith. And that's all for me. Thank you for your attention, and please ask me if you have some questions. And for those who are interested, this is the study that was recently published. Thank you.
All right, very beautiful. And I'll start with a question. So, could it be formed? I mean, could the thermal contraction cracks be formed in the current Mars meteorological conditions? I'm not talking about the ice wedge. I'm just talking about the thermal contraction cracking. And is it the second short question? Is it a relic form, or could it be formed right now?
Well, I think it could, as I said, there is ground ice in the subsurface of Mars, and well, temperatures are at least varying. There is a cycle of seasons, so yeah, why not?
Thank you. And other questions in the chat or?
Okay, can I have a question?
Yeah, sure thing. Go ahead.
Yeah. So you mentioned about the freeze-thaw cycle in Mars. So it's related with the polygons you mentioned. So do you think they still have this kind of freeze-thaw cycles over time, caused by the temperature change?
Yeah. The answer is quite simple. I don't know, but well, we don't know actually. Maybe, but this would be very difficult as on Mars, the temperature is most of the time way under 0 degrees. So the current occurrence of liquid water at the surface of Mars would be involving something like brines or very salty solution, So, well, we think it would not happen with just as it happens on Earth. But again, we don't know what's happening today. It might be different from what happens in the recent past. On Mars, there is always this issue about what is the age of the things you are looking at. It might be very recent, and it might be like a dead landscape, very old. So we don't know.
Okay, thank you.
Welcome.
Thank you. Other questions? Another?
Yeah, sorry, I can't see the chat.
Yeah.
Oh, yeah, okay.
It's empty also. All right, thank you very much for the talk. It was super interesting also.
You're very welcome.
And we're going to the next speaker, Zhenming Wu, from the ExCom, from the PYRN ExCom also, and from the, from the University of Reading, with the topic Permafrost change monitoring using multiple DInSAR algorithms over Arctic Alaska. Go ahead, you have 12 minutes.
Okay, can you hear me and can you see my screen?
Yeah.
Okay, good. My presentation is about the permafrost change monitoring use different DInSAR algorithms over the Arctic Alaska. So we know permafrost is changed dramatically under the current warming climate. So you can see this is the structure of the permafrost. We have active layer, we have ice in permafrost. We also, a huge amount of carbon, organic matter in the permafrost. So as the melting of permafrost, what will happen on the ground? This is, surface heat records from a GPS station over the permafrost region. You can see the seasonal variation, which is caused by the freeze-thaw cycle. And you can see this long-term trend. It's showing kind of subsiding. So what's the consequence? The long-term subsiding, it will collapse the buildings, it will damage the infrastructure. And in terms of the carbon in the permafrost, it will release the carbon into atmosphere, and it will have the positive feedback to the climate change. A recent study also shows that deformation of the permafrost is also correlated with the carbon storage. You can see this is different vegetation types, and this is the carbon. This is deformation over different vegetation types, and this is the carbon storage. They're correlated very well. And so the deformation plays a very key role in the permafrost status monitoring and even in the future carbon modeling. So we found that the traditional methods such as leveling and the freeze-thaw tube, GPR, and also GPS, it has very sparse, the deformation measurement coverage. So we use the DInSAR. This is a technology that can convert satellite image into the surface deformation dataset. So the basic concept of interferometry is if you got surface deformation between two SAR acquisitions, then you can do some process and get the magnitude of the surface deformation. So this is a workflow. If you got a stack of SAR images, then you do some processing. Finally, you could get the deformation map. This colorful map is a surface ground deformation map from the earthquake in Turkey. So those, you see the colorful streams. This is the deformation magnitudes. So DInSAR can measure the deformation from very broad area. So this is also another example from the volcano. You can see this is deformation map of a volcano. This is time series from this black triangle. You can see this area is uplifting caused by the accumulation of the eruption stuff. So especially here, you can see during the eruption time, there's a huge uplift trend. So our study area is in the north of Alaska, and this area represents various tundra types. We also got some in-situ observations from GPS, from active layer thickness, and this is tundra types. Thanks for the last speaker. He already well explained about polygons. So in our study area, you can see the dominant tundra type polygons. It's high center or flat center or low center polygons, and also large lakes and joined thaw lakes. So the data we used is from Sentinel-1 SAR satellite. So the red spots here are represent SAR images we used. So we only use data from summertime is because winter we got snow. It will contaminate the result. So we do interferometry between different SAR images, and then we connect in the entire network, so we could get the time series of the grad deformation of the study area. So we use 3 different SAR algorithms, DInSAR algorithms, PS, SPAS, and EPSIS. They all have different advantages and disadvantages. And for EPSIS, this is first ever used in the Arctic. And here's the result. You can see those ground deformation velocity maps are acquired from different methods and also different observation period. For 3 years, velocity map we get from data from 2017 and 2019, and for 4-year velocity map we get it from 2017 and 2020. So you can see all the velocity maps, they share a very similar spatial pattern, and for the series subsiding area here and here, we find they are correlated well with the river channels. So it's maybe caused by the thaw slumps across the river basins. We also identified some uplift areas in north of the Alaska. So, and if you just look at EPSIS result, it gives a very good spatial coverage than other two methods. And for EPSIS 3-year and 4-year velocity, if you do a simple comparison, you can see we got very serious subsiding in the 4-year result. So we wonder, does abrupt permafrost melting happen in 2020? So it caused the serious subsiding from 4-year observation. And this is the zoomed grad deformation velocity map. So we select an area in the uppermost of the study area and an area in the mouth of river. So you can see still EPSIS, it gives very good coverage, spatial coverage. You can see the subsidence and uplift, and especially for uplift, you can see in this region, uplift is correlated with kind of joint thaw lakes. For this kind of large scale, I think it has never been reported before. So this is a GPS station we used in this study. You can see that around this GPS station we have kind of surface uplift, and here also. So we checked the previous study. We found, yes, this station it does have the uplift trend between 2011 and 2014. So which is agreeing well with our DInSAR measurement. So this is a validation with GPS records for our DInSAR measurements. So we use 3 GPS stations. You can see these green dots are the GPS records. You can see very clear seasonal variation caused by the freeze-thaw cycle. And all the 3 methods, you can see, they all work well. All 3 DInSAR methods work well over the ATQK station. And but only for Barrow station, only EPSIS works quite good. And for the PS and SPAS method, we got this noisy result. And for SG27, this station doesn't have a very clear seasonal variation trend, and also all the methods failed to invert a very accurate ground deformation. And now we go to the assumption we made about permafrost change in 2020. So we compared the velocity rate distribution. We can see the solid lines are the velocity from 4 years observation, and the dashed lines are the velocity rate from 3-year observation. You can see average subsiding rate about 1 millimeter from 3-year observation, and for 4-year observation we found it increased to 4 millimeters per year. So we kind of confirm the assumption of this kind of subsiding change caused by the permafrost melting 2020, but we need to exclude this kind of result is from the SAR images themselves. So we compared the coherence. Coherence is kind of indicator that indicate the similarity of the ground surface. For example, if for the SAR images from same year, you can see they have quite high coherence, which means over the same year the lead surface does not have very significant change. But for the consecutive years, you can see they have quite low coherence. Especially if you look at the coherence from 2019 and 2020, it has very low coherence, even lower than other consecutive years categories. So we confirm that the dramatic growth change happening in 2020. We investigate the active layer thickness change. We found since 2008 we have dramatic active layer thickness increase. Active layer thickness change, it means the melting of the permafrost over the starting area. So all those evidence point that abrupt permafrost melting happened in 2020. So now we go to the conclusions. The abscess show the best performance or accuracy and spatial coverage, and our starting area is degrading slowly with a rate around 1 millimeter per year over the 3 years observation, but it can reach 4 millimeters per year over a 4-year observation. And abscess method can capture the abrupt permafrost melting in 2020. This melting is related to the significant temperature increase in 2020, and it tied for the warmest year on record. Okay, that's all. Thank you. And questions?
All right, cool. Yeah, I'll start with a question if you let me. I know that guys from the column program are also doing things about those subsidence. And did you verify or compare your results with the data from the column sites about those subsidence from Alaska also?
Yes, actually, I compared the GPS. I used the DInSAR measurements against the GPS records. So abscess got quite good result. The actual thickness measurement is due from the COM sites. You can see the active layer thickness is increased since 2008.
All right, thanks. Other questions?
Yeah.
Yeah, just one question in the chat. I would like to know if you have any paper published related with this work.
Okay, I think we will submit it late in this month, but I don't know when it will be published.
All right. Another questions? All right, I have another question also. So all we know that there is a shrub expansion due to climate change, and shrubs are getting higher and they're going deeper. They're going from south to the north. And could the shrub expansion in the future influence on the SAR data or not? I mean,
yeah, I think actually we investigate this kind of effect, but I didn't include them in this presentation. For SAR data, it's different with optical image. So in this research, I use seabed data from Sentinel. So I don't think the shrub in the Arctic will have huge impact on my result. especially if you use the L-bed data. So this kind of vegetation will have no impact on the DInSAR environment.
And another question, what is the vertical accuracy of the method? I mean, just the mistake, because you just mentioned that it's like 5 millimeters per year or something. Yeah, what's the accuracy?
Yeah, it's quite difficult to supply this kind of accuracy. So as I did comparison between the temp series I get from the DInSAR environment, and I use the accessible GPS station to compare the result. It looks quite okay. So yeah.
All right, another.
Yeah, the subsidence rate I mentioned it's kind of average stuff. So.
Do you guys have another questions, or I'll check the chat? Nothing. Also, thanks, Zhenming.
Thank you.
That was awesome. Yeah, and last question from Caitlin Kilker. He is active. Awesome presentation. Will you expand this study area?
Yes, I think so far currently I'm doing some stuff in the entire Tibet. So I collected some results from another, I think, UK Research Institute. They published some infograms from the Sentinel-1. So I think I could take advantage from those infograms and maybe generate the velocity, the Permafrost degrading map for the entire Tibet. So I'm doing it now, but it's quite challenging.
Thank you. Yeah, as Adam guessed, he said that probably will be at least half of the registered people, and here there are 24 people, so it's approximately the half of all people who registered, and I think this is a successful result. And I think, yeah, we need to mention that definitely due to field seasons and another objective reasons, we stop our seminar series and we reschedule it to the fall. And I think it was good 4 seminar series or 3, 4. Charlotte, Adam?
4.
4, yeah. So I think it was useful for all of us, and I want to say thanks for all the speakers. It was very, very interesting. I think that will continue. If you guys have any comments or something that you want to share or discuss, you can do that right now. Yeah.
I think we got a question from the chat. So
yeah. If we have one.
Yes, it's a good question. Why SBAS method does not align with some field stations? I think it's from my experience. I try to investigate this kind of difference. For DInSAR processing, it mainly can be affected by the atmosphere, can be by the soil moisture and vegetation. Actually, I excluded all those the effect. So I think maybe it's because the seabed is kind of maybe affected by the vegetation here, as Wesley mentioned, because we do not have enough vegetation data here. So, and also the algorithm itself. The APSIS is quite new algorithm which is developed by my co-supervisor. So this is very powerful algorithm compared with the SBAS and PS. So for my preliminary result, the APSIS, it shows quite good result, but to be honest, we don't know why. So it's quite complicated for DInSAR processing.
Thank you one more time. And I think we can finish. Yes. Charlotte, do you want something?
Maybe just one more thing. If anybody wants to present their work at our next one of our next PYRN seminars, which we're going to take up again in the fall, I will post a link in the chat so you can go to this Google form and sign up with your name and your topic, and also a brief description of what your topic will be about. So yeah, we're going to take up this seminar series after the summer break. And yeah, hope that it will continue like this with many interested permafrost people. So this has been going on very nicely, and we're really yeah, excited about that everything is coming together so nicely.
Cool. Yeah, I think we're done with the first part of the seminar. Thank you all, and please use this Google form if you want to tell us something. Yeah, thank you. And I think we're done.